all, I'd like to thank to Jamar for this opportunity. As she said, it's very important although you study math, but English is very important because it's a universal language. If you are to work abroad or go to some workshops or seminars, it's very important. So, Jomar introduced myself, but I'd like to say I graduated from here, Santa Maria, some years ago, actually many years ago. After that, as she said, I went to University of Rio Grande do Sul, Porto Alegre, where I did my master's degree and PhD in applied mathematics. And I had two opportunities to study abroad. The first time was in Clemson University, about 10 years ago. And the last time this year, I went to Georgia State University in Atlanta, USA. And I will talk about the subject of this presentation is spectral graph theory. Okay. When the people ask me what is spectral graph theory, I like to play like a game. Okay. Suppose you have your cell phone and is playing some song, and you are trying to figure out who is playing, who is singing, who is named the song, who is named the band. Okay, spectral graph theory is like that. Suppose you don't know the graph, you have a graph, but you don't know the graph, but you know its eigenvalues. Okay, like lambda 1, 2, and you know these values. How you can obtain this graph here? This is spectral graph theory. We also can say spectral graph theory try to discover the structural properties of the graph if you look at the eigenvalues of its matrices. And you have many matrices associated to a graph. Adjacency matrix, Laplacian matrix, distance matrix. All these matrices almost are symmetric matrices. Okay? Another way to say what is spectral graph theory, we can say is combining some tools and concepts of linear algebra and combinatorics. Okay? So, what is the relationship between the eigenvalues of the graph? We have here an example. In this example, if you look at I have two graphs. Both graphs have 5 vertices, and this example special, I'm looking for its Laplacian eigenvalues. Okay, if you look at the graph on the left, its eigenvalues are 5, 1, and 0. And while that, if you look at the graph on the right, its eigenvalues, Laplacian eigenvalues, are 4, 2, and 0. But if you note here, on the left, I have only 1 0. And on the right, I have 2 zeros. Okay? What it means about the graph? What it says about the graph? If you look at the graph on the left, is a connect graph. In other words, it means I have only one component of the graph. And the graph on the right is not connected. If you look at, I have one vertex here. They don't join with the other vertices. In other words, the graph on the right is a disconnect graph. I have two components here. So the eigenvalue 0 give us the number of components of the graph. This is very interesting, okay? So there are many another properties. I can looking for the eigenvalues and say something about the graph, okay? This is just an example, okay? So maybe you are thinking, how is possible to obtain the eigenvalues of a graph? Of course, computing the eigenvalues of a graph is a necessary step, because how you can say something about the graph if you're looking for the eigenvalues? So we need to know the eigenvalues of the graph, okay? If you remember from linear algebra, if I have a symmetric matrix, I know its eigenvalues are real numbers, okay? But if you're looking for another side, it's not easy to find the eigenvalues of a matrix. Why? Because if you remember from linear algebra, characteristic polynomial is a determinant sum matrix. Suppose this matrix has order 10. Okay? How to obtain the eigenvalues of a polynomial has degree 10 is not easy. Although you have many softwares, Maple, MATLAB, now you are using Python, but for a general case, this is not easy, because I have to determine the roots of a polynomial characteristic. Sometimes it has degree much bigger, okay? So there is another way to find the eigenvalues. Yes. In this presentation here, I will show to you guys, we have some linear algorithms that locate the eigenvalues of a graph, okay? For this, we need to use some result from linear algebra. This result is known as Sylvester's law. What says this result? If I have two symmetric matrices are congruent, if and only if they have the same number of positive eigenvalues and they have the same number of negative eigenvalues. This is a result very known from linear algebra. You use this result for obtaining the algorithms, okay? So, how is the idea this algorithm? Suppose we design some linear algorithm that obtain a diagonal matrix which is congruent to adjacent matrix plus xi. X is any value real, okay? So if you get this, and using the Sylvester's law, we can the following result. This diagonal matrix has the number positive entries is the same number of eigenvalues greater than x, and the number negative entries of this diagonal matrix is the same number of number eigenvalues less than x. And another property, very interesting, if in this diagonal matrix you have some zero, that means the x is an eigenvalue of the graph. So using this result and this idea here, you obtain many algorithms for many classes of graphs. We start with working graphs with trees, and after that unicycle, and then we go to threshold graphs and cographs and obtain many results. Okay, I will try to explain how is the algorithm diagonalized algorithm for trees. The idea is very simple. The algorithm, let's put here, maybe you don't know what is a tree. Suppose you have a tree like that. This is a tree, okay? And you want to determine the eigenvalues of this tree. But the idea here is first to locate in the interval, suppose 0 and 2 and -2 and 2. First, you are saying something. The eigenvalues are in this interval or in this interval, or I have to change it for 2, for 3, or for -3s, and so on. Okay? So, how works the diagonalized for the trees? The algorithm, you need to put some value here, x, 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 and x. The algorithm works bottom up on the tree. And the most important, you don't need to look at for the adjacent matrix. Okay? Suppose here is the adjacent matrix. I have something like 0, 0, 0, 0. Okay? So each step on the leaves of the tree, in other words, that means I have 0 on the diagonal. And I move one level above and continue this process until obtain 0, 0, and a diagonal matrix. This is the idea. Okay? So, here we have the diagonalized algorithm in the trees. This algorithm here says we just need to consider two cases. If the leaves have 0, or if the leaves have a value not 0. You just need to consider these two cases here, and the algorithm process gives some estimates and some values for the vertices and move on the tree. The most important, each step behind we are diagonalizing the adjacent matrix, and then after that you use the Sylvester's of law. Okay? Yes.
What does it mean to attribute a value x to some vertex?
Because in fact you are computing, let's put here. You are computing a diagonal matrix which is congruent adjacent matrix plus xi. That means all leaves, all vertices on the tree start with x, some number.
Yeah, but what's
0, 2, any value. And after step, I process and give some value. I will show an example here. Okay. Okay. Here we have example. Suppose I want to locate what is the interval zero, 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 zero. Suppose I want to say something, where are the eigenvalues of this tree? I put here 0 because it's more easy to computing the algorithm. Okay, so if you look at the algorithm says if the vertices have value not 0, we need to enter in this case. But if I have some children, some live with value 0, I need to take these estimates here, -1/2 and 2. So this is the case. I have here 0 and 0. That means the first step of the algorithm is to do that. 0, 0, I have to put here 2, I have to put 6. Doesn't matter, 2 and -2. And after that, we need to remove this edge here. Behind, we are diagonalizing this matrix here. 0, 0, 0, 0, and here I have 0, 0, 0, 0. I have diagonalized this. I have the last 3 rows are and columns are 0. Now I have 0, 2, -1/2, and now I need to diagonalize this matrix here. In other words, now the algorithm moves for these 3 here, and you repeat the process, and finally we have this. So here is the most important. What mean these values? What means these values? I have 2 -1/2. If you are use the Sylvester's law, since we start x with equals 0, that means I have 1 positive, 2 positive, this 3 has 2 positive eigenvalues. And I have 1 negative, 2 negative. These values is not eigenvalues. I just looking for the sign. These values. Negative, negative. I have 3 and 4, 2 negative eigenvalues. What means this 0? Okay, 0 is eigenvalue. So that is very interesting. Why? Because in linear time, it's possible to obtain the eigenvalues of the graph. Maybe you are asking, how about the another eigenvalues? Okay, we repeat the process for another value. Example 1. And if I repeat this process again, some moment I will locate exactly where interval R is the eigenvalue. That is the idea of the diagonalized algorithm. Okay? I'm clear? I hope. Okay. If you look at here, actually, these are exactly the eigenvalues. This is the exact eigenvalues. That means I can, if I put something x2 or 2 or maybe 3, all eigenvalues, in this case, all eigenvalues, I have 3, 2, 1, -3. All eigenvalues must be in this interval here. That means, okay? So, after this linear algorithm diagonalize, we extend for another classes of graphs. Example, unicycle graph is a tree, and you put a cycle. This is a unicycle graphs. And after that, we extend this diagonalized algorithm for threshold graphs and cographs. Maybe you don't know what is threshold graphs and cographs, but threshold graphs are graphs which doesn't contain P4 and C4 and 2K2 as subgraph induced. Okay? Cographs contains the class of threshold graphs. Okay? In this talk, I will just say about, we'll just see the diagonalized algorithm for cographs. Okay? So, how we obtain a cograph? There are many ways to obtain a cograph. One way is obtain a cograph if I take one vertex. If you have only one vertex, K1, this is a cograph. If I have two cographs and take the union, this is a cograph. If I have two cographs and take the join, that means any vertex on this graph is joined with any vertex of this second graph. This is the join. So, using three operations, it's possible to obtain this implied G is a cograph. So, this class of graph is very more complex than trees. Trees is the easy case because we have only few edges, no cycle, is easy to obtain a diagonalize. Okay, but this case is very complex because I have many edges and many cycles. Okay, so how we obtain a diagonalized algorithm? Okay, it's known every cograph has a tree representation. We call this tree by co-tree. Okay, if you look in this example here, on the left we have a cograph, and on the right we have its co-tree. Okay, if you look here, the vertex 1 and 2, they don't have an edge. That means the vertex 1 and 2 are obtained by a union. How to represent this on the tree? I put here vertex 1, vertex 2, and here his father, I put the union. After that, the vertex 3 is a join with the vertex 2 and 1. That means I needed to put the vertex 3 here, and I did a join with the vertex 1 and 2. Using this idea, so on, we obtain the co-tree of this cograph. So, now it's very easy to obtain a diagonalized algorithm because now you have a tree here, and then use the same ideas you have used it for the case of the trees. Then we have a diagonalized algorithm. If you look at this figure here, seems like more complicated than the case of the tree, but works very similar. I just need to consider two cases. If I have leaves with the father is of union type, or if the father is of the joint type, and then process one of the two cases. Okay? Sorry. Okay. I will try to show here example. Here on the left we have a cotree of some graph, and on the right we have the adjacency matrix. Okay. In fact, the implementation of the algorithm, we don't need to use it. We never look for the matrix, but how I'm trying to explain for an easy way for you guys to understand. I put the matrix on the right here for we see what happens when each step of the algorithm is processed. Okay, so the same way on the trees, I have to put x equals 0 on the leaves. Okay, then if the first step of the algorithm is to process the leaves, the bottom up, okay, the depth more below. Okay, so if you look at here, in that case, the algorithm enters in this case here. Why? Because the father of these vertices here is of join of type. Then in this case we must consider 3 subcases, or this, or this, or this. But since we have start with the values equal 0, that means I have to enter in this case here. Why? 0 plus 0 is not 2. Then the algorithm diagonalize process this subcase here. Okay? It's not hard to see. I have 1/2 and -2 as estimates. What means on the adjacency matrix? That means the last row and the last column now is diagonalized. Okay? Now this vertex here must be relocated for this level here, and then we continue this process. Okay? Now this case, the leaves has father with union type. So the union type now I have to enter in this case, and similar to another case, this case of the union has 3 subcases. Then if you look at here, I have 1/2 and 0. It's not hard to see. The algorithm enters in this case here because 1/2 plus 0 is not 0, and then they give these estimates to the leaves. After that, we have to remove one vertex on the tree and continues for the another leaves. Okay, if you look the adjacency matrix, now the last 2 rows and the last 2 columns are diagonalized, and these values I will not process again. Okay, now I have 4 leaves and continue this process. Okay, at the end we have this. So this is the important thing. In this case here, I have 0. If you look at what is the output of the diagonalized algorithm, it's a diagonal matrix, has some values positives and some values negatives and 0. Okay, how many positive values I have? I have 1 and 2. That means this graph has 1 and 2 eigenvalues positive. Why? because I start with x equals 0. And how many negative values I have? 3. That means I have 3, 4, 5. I have 3 negative eigenvalues because I have 3 entries negative. Okay, but I have a 0. I have a 0 on the diagonal. That means 0 is a eigenvalue. So, from using a linear algorithm, we find some eigenvalue of the graph. Maybe you are asking, how about the another eigenvalues? Well, we repeat this process for another x. For example, x equals 2, and try to figure out what's the interval are the positive eigenvalues and the another negative eigenvalues. Okay? In this example here, if you look at the eigenvalues are exactly these 3 negative eigenvalues, these 2 positive eigenvalues, and 0 is eigenvalue, as we showed before. Okay? This is the diagonalized algorithm. Okay. Just a minute. Maybe you are thinking or asking something, well, you have a tool that locates the eigenvalues of a graph, but what is the applications? It's possible to use these linear time algorithms for obtaining theoretical results? Yes. I guess this is very nice because you have an algorithm. You think, well, algorithm give us something you can say is true or is not true, but it's possible to use the algorithm to prove a theorem? Yes, that is one the applications of the algorithm. Okay, so the first application is possible to use these linear algorithms for obtaining bounds for the eigenvalues. You know what is bound? It's possible to say you start the diagonalize for some x if you have all entries negative, all entries negative. That means this x is a bound for your eigenvalues. So Braga Rodriguez and Teresa in the paper published Scred Applied Mathematics 2013, they proved at least half Laplacian eigenvalues of a tree with n vertices are smaller than 2. This is a theoretical result they proved using the diagonalized algorithm in the trees. Okay, so before they use this algorithm for obtaining the sum of the k-largest Laplacian eigenvalues of the tree. Fritzsche, Hoppen, Rocha, and Teresa. Linear algebra and applications. So, another application using these linear time algorithms is to order some spectral prop of the graph. So they use it for proof trees have the largest Laplacian energy. The energy is a spectral property. Imagine you have the eigenvalues of graph. Then consider in absolute value and sum all these values. This output is the energy of a graph. Okay? now you obtain the first result for threshold graphs using diagonalized algorithm. Tá? You use this algorithm to show it's possible obtain threshold graphs with the same energy of the complete graph. Okay. Another application, extremal graphs. Patucci, Freitas, and Delvecchio in linear algebra applications 2013, they prove using the algorithm diagonalized of trees. There exist infinite families of trees with integral index. What means? If you consider the eigenvalues of the graph and the largest eigenvalue we call by index it's very hard to find this value to be an integer number, positive integer number. Okay, it's not easy to find this. So they use the algorithm diagonalize to prove there are infinite families of trees with integral index. Now you are using the diagonalized algorithm of cographs, Allen and me, Discrete Applied Mathematics 2020. Use this algorithm for finding infinite families of integral cographs. You know what is integral? Imagine these are the eigenvalues of the graph. And now suppose all these values are integer numbers. What is not easy. Okay? You using the diagonalized algorithm to find infinite families of cographs with all eigenvalues are always integer numbers. Okay? Another application, Jacobs, Terzan, and me, linear algebra applications 2013. We find among all threshold graphs what is the graph has the minimal eigenvalue. Looking now for this value here. Okay? Consider all threshold graphs and try to figure out what of them has the this minimum value. Okay? Or another graph must be this eigenvalue larger than this. We find this graph. This graph has these forms of 0, 0s and 1s, and moreover we find what is this minimal eigenvalue. This is the minimal eigenvalue. Okay? So there's something interesting about distribution of the eigenvalues. We prove Jacobs, Terzan, and me in linear algebra 2015. No threshold graphs have eigenvalues in the interval -1 and 0. Look, imagine here I have the interval 0, 1, and -1. We prove no threshold graph has eigenvalue here. No. That's very interesting. Why some classes of graphs doesn't have eigenvalue in some subinterval? This is very interesting. Okay? You use the diagonalized algorithm for prove this. Okay? After that, Allen and me, we extend this result for cographs. Okay? If I consider threshold graphs, And cographs is a class that contains threshold graphs. We prove that we have proved any threshold graph doesn't have eigenvalue in the interval -1 and 0. And we extend for cographs, a class much bigger than threshold graphs. Okay? Recently, Gurbani looked for this interval here and he proved that no threshold graphs has eigenvalues in the interval -1 squared 2 over 2. In other words, Gurbani extended. If you put in your computer -1 squared 2 and something like I guess here -1 squared 2, what Gurbani did, he extended this interval. We proved only in the interval -1 and 0 where Gurbani extended the result for an interval that contains -1 and 0. That's very interesting. He didn't use our algorithm, okay? He used another text to prove that. After that, I talked with Emilio Allen. He's a professor University of Rio Grande do Sul, Porto Alegre, and that time I told to him, well, I guess it's possible to use this algorithm for extend for any interval. And we have many meetings. That time it was the pandemic, so we talked a little bit, and after we obtain the following result. Suppose you have numbers n and m, we can generate threshold graphs which are free interval eigenvalues. What means? That means no threshold graphs has eigenvalue in this interval here. It's possible to say how to obtain this threshold graph using diagonalized algorithm. Okay, we extend the result of Gurbani for any interval. Okay, so for finishing, another application of these algorithms, linear algorithms diagonalized, is some problems in combinatorics. Okay, Lazarin, Marx, and me in the journal Linear and Multilinear Algebra 2022, we prove a conjecture about the Laplacian eigenvalues of cographs. The result says, if I have two equivalent cographs with their reduced forms, then G and H have at least K plus some Ti minus 1 Laplacian eigenvalues in common. This is a conjecture proposed for some person some years ago, and you use the diagonalized algorithm for prove that. And finally, as Gilmar said, this year I went to Georgia State University in my postdoc in Atlanta, and I worked with Dr. Xin. He's from China, and he lives many years in USA. And we use this algorithm for the case of Laplacian matrix for obtaining a explicit formula for the number of spanning trees of a cograph. This is the result. For obtaining this result, you need to consider the cograph, look for its tree, and from the tree is possible to obtain the number of spanning trees. This is a very important problem in combinatorics in graph theory. Okay? This bibliograph. And thank you.
Thank you, Fernando. Any questions?
What about the polynomial? It's possible to obtain the characteristic polynomial using this method?
Yes. This is another application. If I have, it's possible using the diagonalize algorithm for obtaining the characteristic polynomial. Okay, but you have another problem. You just have the characteristic polynomial. You have to compute the rows of this characteristic polynomial for obtaining the eigenvalues. So I believe the diagonalize algorithm is more efficient than you compute the characteristic polynomial.
Any other questions?
It's possible to consider some complex eigenvalue?
No. Okay. You working with adjacency matrix, Laplacian matrix. It says that all matrices are symmetric matrices. Okay. That means the eigenvalues are real number, but there are. If I put some directions on the vertices, not the example here, but if you put some orientation, obvious you don't have a symmetric matrix, then you have complex matrix. This is another problem, is more complicated. Okay, but in this case, how to locate the eigenvalues? We need to use the Gregorian cycles. Gregorian cycles says in the where exactly are the eigenvalues. Okay. Any question?
When I apply the value of x, the result of eigenvalue is located before the value of x and after, or
I guess you are trying to say something. What is the input of x?
for example, if I put x equals 1,
Okay.
the eigenvalues will be before them? Or
Yes. Perfect. Suppose you put x equals 1. Then I have 0 and minus 1. I have informations about the eigenvalues are here and here. And if minus 1 is eigenvalue, the negative values on the diagonal says I have eigenvalue less than minus 1. The positive entries on the diagonal says I have positive eigenvalue. I have eigenvalues greater than minus 1. If some 0 appears on the diagonal, that means minus 1 is eigenvalue. That's the idea.
Any other questions? Well, I thank you all for coming, and I thank you, Fernando,
Thank you.
and see you in November the 1st. But we will advertise the next seminar on Instagram. Okay, thank you.
Thank you.